The solutions large group is supersaturated with solution content. So let's not hesitate and get right into the material. We know the basics about solutions already. A solution is a homogeneous mixture of two or more substances. A solution is composed of two parts, a solute and a solvent. The solvent is the medium that does the dissolving. The solute is what dissolves in the solvent. So who can remember what the universal solvent in inorganic chemistry is? What could that be? Oh, that's right. It's water. Water is the universal solvent that we use in inorganic chemistry. So let's take a look at 4 different setups we have here. We have a cell that has sodium iodide in water, copper metal in water, Omaha's air, and then we have a bottle containing kerosene in colored water. And we're supposed to identify whether these are solutions or not. Well, first of all, it has to be a homogeneous mixture. So this first cell has sodium iodide and water, and it looks fairly homogeneous. The sodium iodide is dissolved in the water. This is a solution. The sodium iodide is the solute, and water is the solvent. Here we have a mixture of water and a piece of copper wire. This is not a solution. It is not homogeneous. We do not have a solute or a solvent. Omaha's air is a mixture and it is homogeneous. It is a solution by definition. The main component of the solution is nitrogen gas. It is the most prevalent gas in the air. The other less prevalent gases, oxygen, carbon dioxide, water vapor, those substances are the solute. Like I said, nitrogen gas would be the solvent. In our bottle containing kerosene and colored water, it is not a homogeneous mixture. You can see the separate parts. So this is not a solution. There is no solute, there is no solvent because the kerosene and the water do not mix. So let's get into some specifics about solutions. There are 3 different types of solutions. It's unsaturated, saturated, and supersaturated solution. An unsaturated solution contains less solute than could possibly be dissolved in that solvent. A saturated solution contains the maximum amount of solute that could be dissolved in the solvent at a particular temperature, and a supersaturated solution actually contains more solute than what should be dissolved in the solvent at a particular temperature. The way to test for the different types of solutions is to add a seed crystal to the solution and observe what happens. Let's take a look at the quick demonstration of adding a seed crystal to the 3 different types of solutions. So I'm going to add a seed crystal to this unsaturated solution and stir. And you will notice that after we stir, there will be no evidence that the crystal is there anymore. The seed crystal completely dissolves in an unsaturated solution. Now I'm going to add some to the saturated solution and stir. And you will notice that no matter how long I stir or how much I stir, those seed crystals will not dissolve. If the seed crystals do not dissolve, then it is a saturated solution. So let's add a seed crystal to the supersaturated solution, and you can see upon addition of the seed crystal, we get lots of crystals forming. So when you add a seed crystal to a supersaturated solution, you will observe the formation of many crystals. So just a summary that you can put in your notes: if you add a seed crystal to the 3 different types of solutions, if it is an unsaturated solution, the seed crystal will dissolve. If the seed crystal does not dissolve, it is a saturated solution. And if upon adding the seed crystal, you get the formation of lots of crystals, that is a supersaturated solution. So maybe you're asking yourself, why do all those crystals form in that supersaturated solution when you add a seed crystal? Well, it all has to do with nucleation sites. Nucleation sites are simply places for crystals or bubbles to form. In order for water to boil, or for the crystals to form in that supersaturated solution, there has to be a place for crystals to form. A lot of times this is imperfections in the container. But if you have a nice smooth container, you may not have any imperfections in that container. In order for crystals to form, you have to provide nucleation sites. And adding that seed crystal with all of its little crevices and crannies that might be in that tiny little crystal, you provided places for crystals to form. So let's just really quickly show you another demonstration of nucleation sites and how it would apply to a gas dissolved in a liquid, as is the case for carbonated beverages. So here is salt added to the soda. You can see the salt provides many nucleation sites for CO2 bubbles to form. The same is true for sugar. All those sugar crystals provide nucleation sites for CO2 bubbles to form, and you get lots of fizz. You'll see the sand does the same thing. All the little crevices in the sand provide nucleation sites for bubbles to form, and you get rapid bubble formation. The rag does the same thing. The soda bubbles up and fizzes because of all the nucleation sites possible for bubble formation on the surface of the rag. So just to recap, when we added all those different substances to the Pepsi, we saw lots more fizzing, lots more bubbling. That's because we provided nucleation sites for that dissolved carbon dioxide to form bubbles and come out of solution. So no matter if it was the salt, the sugar, the sand, or the washcloth, all of these items provided additional nucleation sites for the formation of bubbles of the dissolved carbon dioxide. So there's a more famous demo out there about the presence of nucleation sites and their effect on soda. So let's see what happens when we add Mentos to a 2-liter bottle of soda. Okay, pull.